On August 1, 2025, the temperature in Sweihan, a town in the United Arab Emirates, reached 51.8 degrees Celsius. That number is terrifying enough for anyone standing outside in the sun. But for the construction industry that built modern Dubai, the more dangerous number is actually 35. According to the technical advisory notes from the Dubai municipality, concrete must not exceed 35 degrees Celsius at the exact moment it is poured. This creates an immediate and fascinating engineering paradox. How does a city built almost entirely of concrete survive when the environment outside is significantly hotter than the absolute limit allowed for its own foundation to begin forming? We often think of buildings as static objects that only degrade after decades of use. But the danger does not begin when a building is old. It begins in the dead of night, on the very first day the concrete is poured. A batch of concrete that looks perfectly normal to the naked eye might actually be aging at an uncontrollable speed right from the start. This is not a story about skyscrapers melting or sudden apocalyptic collapses. This is an investigation into a silent thermal timeline. It is the story of how extreme heat steals the most valuable resource an engineer has. To understand this invisible threat, we have to stop thinking of concrete as liquid stone that simply dries in the sun. Concrete does not dry. It cures through a complex chemical reaction known as hydration. When cement mixes with water, a violent molecular transformation begins. This reaction naturally generates its own internal heat while forming the microscopic crystalline structures that give the material its immense strength. When you place this chemical reaction inside an environment that can easily exceed 40 degrees Celsius, the entire process goes into dangerous overdrive. Heat does not just make the concrete hot. It steals the exact amount of time required for the material to form correctly. The American Concrete Institute clearly outlines the risks of hot weather concreting in their technical guide known as ACI 305R. They warn about rapid slump loss, which means the mixture becomes stiff and unworkable much faster than intended. The water required for the chemical reaction begins to evaporate into the dry, hot air before it can bond with the cement. A truck driver navigating through city traffic is suddenly racing against an unforgiving clock. A crew waiting for the concrete pump suddenly has a severely shrunken window of opportunity to place and finish the material. If they force the stiffening mixture into the structural forms, they risk leaving microscopic voids. But the most severe consequence of these stolen minutes will not be visible to the workers on that day. The consequence of this rushed chemistry might only reveal itself after 28 days have passed. There is a common misconception that concrete which hardens quickly is somehow more efficient or stronger. In the harsh climate of the Gulf, rapid hardening is actually a mechanical illusion. Industry literature and material science testing provide a sobering perspective on this. Data shows that if concrete spends its first 24 hours curing at elevated temperatures around 38 degrees Celsius, its long-term strength suffers. When these hot cured samples are tested in compression machines after 28 days, their overall compressive strength can be 10 to 15% lower than concrete cured under standard controlled conditions. It is crucial to note that this is laboratory test data, and it does not mean every building in Dubai is missing 15% of its strength. Engineers design structures with massive safety factors to account for variables just like this. But it reveals a fundamental truth about the physics of the material. Hot concrete might look stronger and harder on the first day, but it is fundamentally weaker on the day its true strength is finally tested. The chemical bonds are simply formed too quickly and too chaotically to achieve their maximum potential density. However, a slight reduction in overall compressive strength is not actually the most dangerous path of destruction. The structure can usually handle that loss without compromising safety. The much more dangerous path is physical, and it is often only as wide as a single strand of human hair. When concrete loses moisture too rapidly under the intense sun, it shrinks. This plastic shrinkage violently pulls the material apart before it has even gained enough strength to resist the tension. The result is a network of microscopic fractures across the surface. A crack is not the final result of the destruction process. It is the exact place where the true destruction process actually begins. A detailed study titled Durability of Concrete in the Arabian Gulf, authored by Mufid al-Samarrai, highlights exactly why this environment is so uniquely brutal. The research aggregated tests observing concrete behavior at 20 degrees, 40 degrees, and 50 degrees Celsius. For certain concrete mixtures with specific water-to-cement ratios, the width of the cracks increased by 20 to 40% under the hotter conditions. Again, different mixtures react differently, and modern engineers use chemical admixtures to fight this. But when those cracks do form, they change the entire physical destiny of the structure. If we could shrink down and fly a camera into one of these microscopic canyons, we would see a terrifying reality. These widened cracks bypass the dense protective outer layer of the concrete. They create direct, unobstructed highways leading straight into the dark heart of the structural columns. And what is waiting at the end of that highway is the very thing keeping the building standing upright. But the cracks alone are harmless, without an invading force, because temperature does not act alone. Dubai sits on the edge of the sea and the edge of the desert. This geographic reality creates a punishing daily cycle for construction materials. During the day, the brutal sun bakes the surfaces and expands the materials. At night, coastal humidity rolls in, blanketing the city in thick moisture. The wind carries fine desert dust that is naturally laced with heavy concentrations of salt and chlorides. Heat is not the sole assassin in this story. It is the accomplice that makes every other mechanism of degradation work faster and reach deeper. The elevated temperatures act as a biological catalyst for chemical decay. Every time the temperature rises, the kinetic energy of the water and chloride ions increases. They move through the microscopic cracks with greater speed and efficiency. The heat accelerates the evaporation, leaving behind concentrated salt deposits deep within the pores of the concrete. When the humidity returns, that salt draws in more moisture, creating a highly conductive chemical soup. The heat ensures that any flaw, any tiny shrinkage crack or poorly vibrated section becomes an open door. The salt, the water, and the oxygen are simply the soldiers walking through the doors that the temperature kicked open. And the ultimate target of this silent invasion is not the gray concrete that tourists photograph. The concrete you see on the outside is merely protective armor. Its primary job is to maintain a highly alkaline chemical environment that surrounds and protects the steel reinforcement bars hidden inside. This alkalinity creates a passive film over the steel, completely preventing it from rusting. But as chloride ions from the salty coastal air travel down those heat-expanded cracks, they slowly poison this alkaline environment. The National Institute of Standards and Technology, known as NIST, has extensively modeled how chlorides ingress into cracked concrete. Their studies confirm that cracks fundamentally alter the transport path, allowing chlorides to bypass the slow diffusion process. Once the chloride concentration at the depth of the steel reaches a critical threshold, that protective passive film is violently destroyed. The steel rebar begins to corrode in the darkness. This is where the physics turn against the building. As steel rusts, the byproduct of that corrosion expands. The rust requires significantly more physical volume than the original steel. This expansion generates massive outward pressure from inside the concrete column. The internal pressure becomes greater than the tensile strength of the concrete itself. The armor begins to push its own skin away. The visible concrete on the surface is not the most important victim. It is simply sacrificing itself to protect a skeleton of steel that we cannot directly observe. This entire process happens in absolute silence, hidden behind polished hotel lobbies and pristine retail facades. This delayed invisible reaction creates the most terrifying phase of the building life cycle. A structure does not need to lean or sway to be in a state of advanced degradation. The external functions of a luxury tower can operate flawlessly, while a microscopic war is being lost inside the load-bearing walls. Fresh paint, premium cladding, and decorative panels easily hide the earliest signs of internal expansion. The chloride ingress is a cumulative historical process. It silently records the mistakes made on the night the concrete was poured years ago. This is exactly why structural decay cannot be assessed by the naked eye. When specialized inspection teams are called in, they do not just look at the surface. They use ultrasonic pulse velocity machines to send sound waves deep into the columns. They deploy thermal imaging cameras to detect hollow spaces where the concrete has detached from the steel. They measure half-cell electrical potential to map the active corrosion current flowing through the rebar. They drill cylindrical cores out of the walls and spray them with chemical indicators to measure exactly how deep the carbonation and chlorides have penetrated. Structural degradation rarely begins as a sudden cinematic disaster. It begins as a massive, invisible maintenance bill that no one has seen yet. But the strongest evidence of this thermal threat is not found in a broken piece of concrete. If the extreme heat of the Gulf was just a minor inconvenience, the construction industry would not have reinvented its entire logistical foundation to fight it. The Dubai municipality mandate, keeping concrete under 35 degrees, is incredibly difficult to achieve when the ambient air is 45 degrees. The American Concrete Institute provides detailed methodologies for successful hot weather concreting, and the solutions are staggering in their scale. Engineers cannot just add cold water. They build massive industrial chilling plants just to produce shaved ice to replace the mixing water. They construct giant shading structures over the mountains of gravel and sand to block the direct solar radiation. They paint the mixing trucks stark white to reflect the sun. They inject liquid nitrogen directly into the concrete mixtures to aggressively force the temperature down. They schedule the most critical pours for the middle of the night, deliberately altering the sleep schedules of thousands of workers. When the concrete is finally placed, they immediately cover it with wet burlap and plastic sheeting to trap the moisture inside. The clearest proof of the attack from the heat is the sheer scale of the system erected to defend against it. The industry is spending millions of dollars just to trick the concrete into thinking it is being poured in a temperate climate. But an elaborate defense system is only as strong as its weakest logistical link. This massive cooling operation brings the human element back to the center of the tragedy. Translating material science into daily operational reality creates immense psychological and logistical pressure. For this defensive system to work, every single link in the chain must execute flawlessly. The aggregate must be perfectly chilled. The chemical retarders must be dosed exactly right. The truck must leave the batch plant on time. The construction site must be completely prepared to receive the material immediately. The concrete pumps cannot jam. The workers must vibrate the mixture perfectly to remove air pockets before it loses its slump. The curing blankets must be placed the second the finishing trowel leaves the surface. If a truck gets caught in unexpected traffic, the temperature inside the spinning drum begins to rise. If a strong, dry wind sweeps across the exposed top of a newly poured slab, the surface moisture vanishes in seconds. The workers are suddenly running a desperate race to save a chemical reaction that is rapidly accelerating out of their control. The true opponent of concrete is not just the temperature itself. It is the critical time that the temperature violently subtracts from the human operators. When one truck is delayed or one curing blanket is forgotten, the vulnerability is permanently baked into that specific section of the wall. At this point, it is absolutely vital to look at the reality of the city skyline. The extreme heat is not an automatic death sentence for every structure in the emirate. The research from Al-Samarrai explicitly notes that many reinforced concrete structures in the Gulf have survived 30 to 40 years or longer without requiring major repairs. When the mix is designed perfectly, when the cover depth over the steel is thick enough, and when the curing process is flawless, the concrete can hold the line against the climate. There are masterfully built towers in Dubai that will stand strong for generations, but the same research also documents severe cases of early structural deterioration in other buildings. This lack of uniformity is exactly what makes the situation so complex. The tragedy is not that every building will collapse at the same time. The tragedy is that they are all aging at completely different speeds, which the human eye cannot distinguish. Two hotels that look exactly identically luxurious on the outside might have entirely different structural destinies. One was poured on a cool night with perfect quality control. The other was poured during a July heat wave where a delayed truck caused a series of micro cracks on the western facade. That difference in quality does not cause the second hotel to fall down. Instead, it transforms the environmental temperature directly into a severe financial penalty. This is where the invisible chemistry becomes a visible economic burden. A hot summer day in Dubai only lasts for 24 hours, but the structural consequences of a poorly cured batch of concrete on that day will require mitigation for decades. When the steel begins to rust and the concrete begins to spall, the building owner must pay a heavy material tax. Workers must erect scaffolding around the affected columns. They must use jackhammers to aggressively chip away the contaminated concrete until they expose the rusted steel. They have to sandblast the rebar to remove the corrosion. They must apply advanced chemical rust inhibitors and then painstakingly rebuild the missing concrete with specialized repair mortars. This process is incredibly loud, deeply disruptive, and extraordinarily expensive. For a city built on the promise of flawless luxury tourism, this poses a massive operational crisis. You cannot maintain a 5-star hospitality brand when your guests are waking up to the sound of concrete being chipped away from the balconies. Every dirham spent repairing early corrosion is money drained from the economic efficiency of the property. Dubai is not merely surviving a hot summer. The city must finance a relentless maintenance regime that will last as long as the buildings themselves. The heat creates a permanent baseline of economic friction that constantly eats into the profitability of the real estate and tourism sectors. When you zoom out from a single microscopic crack to the scale of an entire metropolis, the true nature of the battle reveals itself. The designed service life printed on an engineering blueprint does not automatically translate into reality. Service life is earned through flawless execution on the ground. It is dictated by the thickness of the protective cover, the density of the vibration, and the timing of the wet curing. The extreme heat dramatically narrows the window for human error. It ensures that mistakes are immediately punished by shrinkage cracks. Those cracks drastically shorten the distance the chloride ions must travel to reach the steel. The subsequent corrosion makes future repairs exponentially more complicated. This creates a relentless mechanical treadmill for the city. On one side of the street, massive cranes are pouring thousands of tons of fresh concrete to build the next generation of luxury resorts. On the other side of the street, diagnostic engineers are using ground-penetrating radar to find the hidden rust inside the towers built 20 years ago. The ultimate threat to the city does not lie in the towering height of what is being built. It lies in the shrinking distance between the speed of new construction and the speed at which structural damage must be detected and repaired. The system is built for endless growth, but it must drag an ever-expanding anchor of maintenance costs behind it.